Start the stream, 9:30 on a Friday. Let's see if this works. Always the best words possible when you're running a class. Hey, did it work? Hey, welcome back, everybody. Good to see you. I'm a little bit frazzled, like normal, but probably a little bit more than normal. I got back from the conference on Tuesday, and ever since then, I don't think I've had 10 minutes on email. So I'm really, really slow. If you write emails, I apologize. But I will get to you, hopefully by the end of the day.
How was the conference?
Terrible. No, I'm just kidding. It was fine. It was fine. The place where I usually go to just NCME, and the place where it was under construction, which made it hard to mingle very well with people because the main floor was all under construction. I don't know if anybody else who was there could have an opinion on that. But anyway, a couple announcements I'd like to make. If I get my act together, you'll see these over email, but I wanted to give you opportunity to put some placeholders in your calendars just for things that are coming up. First, 2 weeks from today in the afternoon, Dr. LeBeau and Brandon and I, will be part of a presentation on how to use the high performance computing to do a lot of your work. And part of it would be really, really good for this Bayesian stuff. So if you are thinking of doing research with Bayesian, you know how long it sometimes can take to run the models? This is where our campus server and cluster does a really good job. You submit a job with your data, it schedules it. Yes, it may not run immediately, but it'll run at some point. Plus, you can run multiple iterations of simulations. And so this is going to be a college-wide seminar, talk, something. Dr. Alloway helped organize it. So thank you. Part 2, I believe, Monday, May 6th, it looks like. There's a visiting professor from computer science who may be over here to give a talk on using neural network type models to estimate IRT models. So just like a research talk, nothing super major, but it'd be great to, if you're interested in sort of where things are at with weird machine learning techniques plus stuff that we know a lot of already with IRT, it might be good to see. So I'm looking forward to her talk as well. So just give you the heads up before, again, once I get my act together. It's on my to-do list right now has like 38 things on it that are overdue. So it's just one of those I've given up type days. But we do have a lecture day. So those are the announcements. Homework due this evening. If you can't make this evening, I'm not going to cry if you wait till Sunday. I won't cry about it because reality is I'm not going to be in town until Sunday, and I won't even be able to grade them this weekend. So just blanket heads up. If it comes in, you know, by the end of the day, whenever that happens to be Sunday, and what I define that as is before I wake up Monday morning. Totally cool.
Is this the CFA homework?
The CFA homework, yep.
Okay.
Yeah.
I was super worried for a second.
No. We have a new homework coming out. That's the problem. We're sort of, because of the way I've done this class and it's sort of dragging to an end, there are 2 more homeworks left. One has come out today. But you're going to see that CFA and IRT are going to be very similar in how things look. So it's not going to be bad. And actually the data for this homework I'm really aware of because it was in one of my papers, a couple of my papers, and it's in one of the packages in R. We'll talk about that later in class. Any other questions or thoughts from you? The few? All right. Should probably check the world. Anyone on there? Hello, world. Let's see if I say hello. Anyway, so I did try it in my quest to, I'm never happy with the way things have run in RStudio, and that's part of my feelings of unease with this class. So I tried again, something new, and I don't know how this will work, but if you grab the files from the website for today, you'll notice in the file section there is this rpres file. That is an R Markdown file that RStudio developed that creates a presentation. And I'm going to try to walk through that at least in the beginning to use it in RStudio while I'm doing everything else. Now, it's not a big or awesome, amazing presentation because, well, again, if you've got a to-do list, like right now, this is one of those acute times where like getting anything done seems impossible. I've got the basics of what I'm going to talk about in here, but then I have an example file that is in R Markdown right here, this R Markdown file. Now, I will tell you, if you run this file, you better wait. It may take you 30 minutes to get through to run the whole thing. So there is the HTML version of this file in the folder, and I am going to be using it. You can open it in a web browser. So I ran it all, it's up in HTML. I'm going to be talking about it on HTML here, but that's just because we're getting into classes of models where things start to take a little bit longer to really run, and that's how it goes. So, cool. If you want to see the presentation in your own RStudio window, once again, open up the rpres file. Usually you just go up to the beginning, hit preview. It should show up in the pane by environment with the word presentation, and you can just go through it. Now, I haven't played around with this enough in the styles or themes, so this is like the default theme, which makes me cringe a little bit because I love style, like I love design that way. If I wasn't doing this, I'd be an art major. Just kidding. But cool. All right, questions, comments? Okay. So now we're going to do IRT. We did CFA for the last month, maybe month and a half, I don't know. But yet we're making our way around the other paradigms of psychometrics. And the nice thing about IRT is the CFA kind of broke us in on the hardest parts of things. IRT is not, there's some catches that make it uniquely interesting, but in general, it's not all that different from CFA. But today, I've broken up IRT over 2 weeks. Today, we're going to do IRT for binary data, mainly because it sets a very good use case. I'm going to do unidimensional and multidimensional within binary data. And then next week, we're going to do ordered categories of some sort, maybe multinomial as well. Next week probably will be split between that and talking about theta a lot more, like our estimates of the latent traits. So I'm going to have a chance to go through there, assuming I, make it through the to-do list. We'll see. So let me see what I can do to begin here. Not used to having slides again. This is amazing. We're going to talk about, I just said all this. Comparisons to CFA. Here is just a real quick overview of an IRT model, just to get us into the right structure. This is a 4-parameter logistic model, and I threw 4 parameters at it because you can quickly make constraints on these and get models that are subsumed by it, right? So, familiar to everybody? Okay, logistic link, right? Probability an item is equal to 1, given theta. You've got C is your lower asymptote, which I keep wanting to call guessing, but I really cringe when I call it guessing. D is your upper asymptote, and then you've got this term in here. This is an inverse logistic link, and inside the parentheses, you've got a discrimination parameter and a difficulty parameter. And I put the ranges on here. One small note I'll make, it does show up in CFA a little bit, but it's more often, I feel like, in IRT. The range of A, I like it to be negative infinity to positive infinity. Do you remember what happened when we, so A is the analogous parameter to our factor loading. In fact, in just a couple seconds, I'm going to flip this over into a different parameterization. By the way, this is parameterization we often call discrimination difficulty. It shows up in unidimensional IRT, but then quickly goes away for almost everything else. What happened in the loadings in CFA in our example? The first time we just rolled it off the shelf.
We ran into non-uniqueness issues.
That's right. Turns out that happens a lot in IRT as well. So even though it makes me cringe because I want to have that be a range of negative infinity to positive infinity, today we are actually going to restrict this from 0 to infinity by putting a log normal distribution for its range, prior distribution on it, which will keep it from going below normal. Thoughts, questions? So I'm assuming everybody's like, yeah, IRT, I love it. A couple other notes I wanted to make you. Unidimensional IRT model. I read this sometimes too. These are more pet peeves. IRT assumptions. People, or in my other university, I don't know about here, would say, oh, IRT assumes unidimensionality. And I would always say, no, unidimensional IRT assumes unidimensionality. So just a phrasing that you want to make sure that you understand. Yeah.
Can you say 2 words about D? Because the old people like me, when I was in school, we went up to 3, and 4 came later. So
I understand D came actually in the late 60s, early 70s. Yeah.
Sure, popularity was.
Yeah, oh, popularity, yeah.
Yes, it wasn't really used in the early 2000s.
I'd say this about C too. C and D are fudge parameters. They basically say, I believe this is happening. You basically with IRT, I think, at least my philosophy is this, particularly for the data we're going to have today, which are constructed response items. Hard to guess, right? You really think this is happening in IRT, but your data suggests otherwise. This is a quick and easy way to try to make the data work more cooperatively, right? The C parameter with the lower bound changes your what the model does for information available for data, right? Shortens that range that you can have, shortens the, in theory, makes the slope a little bit flatter, so it's harder to get estimates of data. So if you think about one of the things I always rail on, probably in here, is that actually in my life, I get teased about this by a lot of people now, and the friends I have at NCME, which was reliability depends on model fit, right? If you ignore sort of misfitting things in your data, with C and D being different than 0 or 1, respectively, would give, then you're going to overestimate your reliability for data, and that's what these do, they sort of bring it down. So they're real quick fudge factors, I like to call them. They really have no, it's hard to see a theoretical basis for D. And C, in some use cases, you may say, yeah, I have a theoretical basis for it.
Like multiple choice items, C kind of makes sense, but even then, it's rarely ever equal to 1 over your number of options.
Exactly, right. So there is some non-zero chance of guessing on an item. It's not like, what's the old adage, given a typewriter and even a primate can produce,
full of monkeys,
yeah, produce Shakespeare enough time, right? It's like,
see, conceptually, see, I can see why you want the lower asymptote to be higher. Conceptually, I struggle with the idea of D, why you want the upper asymptote to be lower.
So I believe, I attribute, and maybe this is a misattribution because I'm forgetful, but I attribute D to a person who was my first teacher in psychometrics, was Rod McDonald. And I feel like he had some of the early studies. So he may roll over in his grave for saying this, but whenever you see a 1 there, it was a pretty easy fix to go put a D there, in theory, to draw it out. Now to go estimate it back when I think he did it, probably a lot harder. But it was one of those, I'm not sure where this is going to go, let's try it out. And now for me, it's just, it's a general model, it's subsumed by things. I've never used it in my life. Don't think I will. It just sets what I'm trying to do with these slides is set the most complicated case, and then we're going to go fix things and use the more easy case after that. So I don't even use it in the example coming up. Good question though. Other thoughts or questions?
I think even when a lot of us took IRT with Dr. Colin this year, he didn't ever talk about D.
No, I've never seen a use case of D where I was like, oh, that totally makes sense.
Really?
Wow, whoa, that's amazing. Well, if you think about it, there's another, in Dr. Colin's class, did you ever cover unfolding models? Okay, so there's another class,
No.
In this place, we don't have any paper towels.
I can take it out.
All right, no problem. I'll take a pause here for a second. Let's take a deep breath.
Frustrated with the D parameter.
I know. You don't want to watch your bag or your shoes. Just make sure you're not getting wet there. Okay.
Or you can smell like coffee all day. I'm going to anyway.
Oh, no. Well, if you really want to make it worse, just go have some beer at lunch.
Yeah,
smoke a cigarette, have a beer.
Grad school.
That's right. Getting the early start on the weekend. That's exactly right. So there's this class of models called unfolding models, or ideal point models. And really what those are models that take your item characteristic curve and make it non-monotonic. Right? And you're like, why would you want to do that? And from coming from the perspective of IRT, I sort of think of that's sort of model fit. But if you look at a lot of work in like political science or some type of attitudinal attitudes towards certain beliefs that may or may not be popular, you may have try to scale them on a dimension. I had a colleague at the University of Georgia who started there as I was leaving, who's fairly well known in political science, Keith Poole, and I was actually trying to use some of his data for homework this week, but it was trying to order people of Congress and bills based on conservatism versus liberalism in IRT, and that's a case where, from the IRT perspective, in certain regions the model doesn't fit very well, and so that's where if you allow non-monotonicity on certain sides, you get a better fitting model. But what is that?
Or like the confidence versus ability.
It also could be there, yes. Yeah, so it's a tough. Anyway, I'd love to go more into those models as well because they're really fascinating, but they're not. I don't see a good use case for just like D, also. The other part that I have here, and by the way, I say that I don't see a good use case. I'm trying to leave open the possibility it's there. So if I'm saying that too strongly, I haven't yet seen one. Maybe I should say. That doesn't mean that I've seen everything, and it doesn't mean that there isn't one. But I think it'd be probably a narrow use case that would be out there. But that's just my ignorance with literature.
Well, like a traditional academic educational setting, if D wasn't one, your item's probably not doing well for your population.
Yeah, that's right. Yeah, there's something going on with your item that's not good, most likely. I also allowed theta to have a variance and a mean here. Now, this is just as it is. If we try to estimate everything, it's unidentified for a number of reasons. One being we have to do something to identify the scale of theta, either set things or move things forward or fix that to 0. Actually, that's what we're going to talk about here. So the structural model in IRT, and there is a structural model, and I'll bet people here know that, whereas other people I've talked to in other worlds didn't. IRT is not the case where we always set the mean to 0 and the variance of theta to 1. And I say that because in multidimensional CFA, if you remember, when we went to do the covariance matrix for theta, we had to go and use a Wishart prior for the inverse covariance matrix, actually. And that allowed, that estimates the whole covariance matrix. So we have to come up with a way where we identify it such that that covariance matrix is estimated, or we have to standardize in each step. And I prefer not the standardization in each step because there are other problems that could be hidden by that, I feel like. So I try to keep things as real as I can with the data. So Bayes is a place where this theta parameter and this mean, the mean doesn't really show up too often until we get into like what we would call measurement and variance in the CFA world. But the variance itself would be a big thing. Wow, where did you find that?
Patricia.
Oh, Patricia, the patron saint of our program,
It's like,
of our department.
CBS.
Like, oh, the one. I got it. Just keep it.
Wow.
Thank you.
Muchas gracias. Thank you very much. You want me to do that instead? Oh, wow. Full service. Okay, so to do this, I just, again, laid this out as general as possible. The structural model, you have for the latent mean, you can either set mu equal to 0. All right, basically, you need to make one constraint on the mean or the b's. All right? And technically, it's actually not even the b's, the b parameters. You can get by once we go to discrimination difficulty. Once we get away from that, once we go to Slopeintercept, you'll see that we can actually do part of the b. It's sort of what an intercept might be, or a threshold. So if you really wanted the mean, you could set, like, for instance, one item difficulty to 0 by fixing the item difficulty scale. Then all of a sudden the latent variable has a mean that we can go and try to estimate. And then, or you can do things like a sum to 0 constraint, where pick one item difficulty and it's equal to -1 times the sum of the rest, right? But either of those constraints will do. And there's probably more than that even that are out there. Latent variance works the same way. Instead of b and mu, though, it's a and theta. I'm sorry, sigma squared theta, right? So you can fix sigma squared to 1 and estimate all the A parameters, or you can do some constraint on 1A, at least 1A, and estimate sigma squared. Right? And so you may see this, there's some, actually don't even like get involved in this because it makes my eyes roll. It's sort of the minutia that people want to say, what's the difference between a 1PL and a Roche model, right? But you know what I'm talking about, right?
Yeah.
I sort of just go, yeah, whatever. None of the unrealistic models for data. And have you gone to Roche.org? Have you ever gone to this website? So this is part of my shtick in the world. Yeah, hey, Lisa's listening. Hey, Lisa. Shout out to Coralville, Iowa. Hope you're feeling better. Yeah, multidimensional CFA is not a thing, exactly. If we go to Roche.org, there is a website, and they have a most wanted list at the bottom, and my face is right on there. No, I'm just kidding. This is a website that's, maintained. Roche-friendly journals.
Oh my gosh.
Definition of measurement. Like, I'm serious. Like, board of directors. Board of directors. No, Jack Sinner. Oh, he's at Metametrics. If anyone wants a job at Metametrics, the Lexile is a Roche scale. Kid you not. Anyway, so.
We're making fun of it, but that's a good thing. Because it's a nonsense model, right?
It is. It's sort of one. I guess technically speaking, we could say let's let empirical evidence bear itself out. The problem that I have with Roche is if there's a problem, if the model doesn't fit, it's not the model's fault.
Your data.
Your data.
Yeah.
Data do not compute here. This is bad.
That's your data.
Right. So
Students cheat.
To reach us other places. Yeah. So anyway, Roche.org. 1990s technology website, 1960s technology model. Sorry, where am I going off with Roche? Anyway, sometimes, I'm getting into the parameterization different, but sometimes you'll see one parameter logistic model, I think it's safe to call it that, where you estimate a common discrimination parameter. Maybe you fix the variance of theta to 1. Technically speaking, in that case, because you've already made a constraint on the A parameters, you could actually estimate a variance too. Now, I don't know if that's Roche-ish or not. I don't know if that's on the OK list. We were just talking about the cult of Roche. I like this one the best, which was Roche-friendly journals. Roche.org has Roche-friendly journals. All right. There we go. Okay, so back to the fun. You can, the configurations we do. We can get a 1PL if for every item C equals 0, D equals 1, and either fix all the A's to constant, get a variance of 1, or fix all the A's to 1, estimate the variances are equivalent. 2PL, so fix all the C's to 0, all the D's to 1, and then something about latent mean and variance with A's and B's. 3PL with the D of being 1. See, this is why I did all the 4-parameter model, and halfway through I'm like, why the fuck did I do this? Right? All the D's to 1, figure out, estimate all the C's, and then something with A and B for a latent scale. And then the 4PL, oh my goodness, yeah, right, okay. Have you done much with unfolding models? Okay. All right. Different models. We can change things around. We can go with the core. Sometimes I call this a kernel. Sometimes I call this a core. This is sort of the Logit part of the logistic item response model. But I'll say core because we can switch this part. This is what we call an inverse Logit or inverse logistic length function. Right? It converts a Logit or a continuous number into a probability. Yes.
Yeah, I was just going to clarify that. A length function by definition is one that takes
a bounded number,
yeah,
puts it on the real number line, or not necessarily bounded.
Right.
Yeah, it takes a function of a moment of the data usually, typically the mean, right? So the mean of a Bernoulli variable is a probability. We apply a length function. In our case, log of probability over log of the quantity probability over 1 minus probability. Log of odds converts probability to continuous real number line. This works backwards. Takes continuous, which is up here in the kernel or core, puts it on the probability of mapping. Thank you. Did I say that correct?
Yeah, absolutely.
Then you have the inverse normal ogive link function. So we have an ogive link function, ogive, ogive. Yeah, that. I don't know about that. Where'd that word come from? Hey Siri, define ogive. Really?
Well, mostly we said it doesn't matter because you can scale the logistic so that they're less than what 0.001 from each other.
Yeah, 1.7, and then depending on who you talk to, 2 or 3 more decimal places. Again, Rod McDonald's 1.701. Right, the extra 1,000. Yeah, 10,000. Yeah, one extra 1,000 made a big difference, evidently, to Rod. Sorry, Rod. Anyway, sorry. I really appreciated Rod. He was fantastic. I knew him ever since 1998 until he passed away, and he was really tremendous in my development as a human. Yeah.
If you guys never seen his book, it's something that you guys should read. I don't know if you guys get exposed to the book in class.
Yeah, Test Theory Unified Treatment. It's really a great text. Thank you. Yeah, it's interesting. Anyway, so yeah, you hear, okay, we can switch between the two. Now in Bayes' world, there is a huge difference between these two, and that difference comes in estimation, in speed of estimation. So in 1992 and 1993, there were some papers that came out, not for IRT yet, they came out shortly after that, but that did for logistic regression. And they said effectively, for a logistic regression, so when we did normal, when we had a regular linear regression, when we assumed the data were conditionally normal, we could quickly show, and some of you had to do this in your homework, conjugate prior, how conjugate prior work. And conjugate priors are awesome, why?
Because it makes estimation a lot faster.
Faster and efficient and la la la. Well, flip that conditional normal assumption and say, now I'm going to go model the probability of some type of success, if we will, in a Bernoulli, a single trial Bernoulli. And all the math that we did before that was enabled because we had this nice normal distribution goes away, right? So in 1993, there was a paper by 92 or 93, pardon me, Albert and Shib in JASA, Journal of American Statistical Association, that showed there was a way we could do effectively logistic type regressions, although it's with an ogive link with Gibbs sampling, right? And so the way that they came up with is something called the data augmentation procedure, which effectively took your data and simulated for each response a continuous underlying response that had a bound to it. Right? It was either, if you had a 1 in your data, your bound was, lower bound was 0, upper bound was infinity, and the other half of it for the other way around, for 0. And what they showed was, when you have that underlying variable, if you use it in the MCMC algorithm, you can do full Gibbs sampling like you would with a linear regression. The catch being you have to keep simulating that variable as well. And it really made things go amazing. It's just fantastically quick. Like night and day different. So you'll see a lot of IRT in Bayes right now with probit for that reason, with the ogive functions, because it does speed things up. And all of my examples today are there. Now, that was the 90s. Technology has enhanced. There was a couple key papers that came out. I was just reading these on the plane when I was tired coming back from Toronto, just because that's my hobby, I guess, right? 6:30 in the morning. oh, this is awesome. I'm waking up with this. Anyway, they showed how, one of them showed how to do the Gibbs sampling for the ogive a little bit better with the way that you do this underlying variable. And then also showed how you could do a similar process for the Logit. But the Logit had a catch. It was kind of like a generalized least squares, but you had to estimate a variance parameter, but you can only do that, or set of variance parameters. You can only do that with part of it with Metropolis Hastings. And then in 2013, this massive, awesome paper came out that had a family distribution called Poila Gamma. Distributions, they're really complicated kind of mixtures of gamma and continuous variable distributions. And they showed how you could do that similar approach that the 92 paper did, the augmented data approach with the ogive itself. And actually a student from Kansas, Jehan Zhang, and myself are on a paper that's about to come out in Psychometric doing that with IRT. So there are other ways that you can do this now faster, better. But it's still incredibly difficult to implement in many ways because the calculations for Poila Gamma are really slow. There's like layers of simulation that you have to do to get it to work, but it's still out there. So anyway, I make that note here because often, and actually whenever I've taught IRT, yeah, I'm gonna pick one and there's 1.7 times the Logit and you can get, you know, ogive back. But really, for what we do, ogive is probably the most that you see in the Bayes world.
I'm not thinking straight.
I think Kirby.
I'm trying to think what the X in your logic represent.
This should be, this is actually, no, I've got this wrong. This should be dx right here. It's the variable we're integrating over. My notation's off. My apologies.
I keep looking and I'm like, well, what I'm not seeing?
No, this is me screwing up notation. My apologies. Do I get at least a little credit if I screw it up? I'm like, oh yeah, that should be this. Oh, right? Yeah. Okay. So it's like, you'll forgive the mistake. If I'm like fundamentally, oh, Z, yeah, that's pretty.
Mario's like, what about this? And you go, oh my God, I have no idea.
Yeah, well, I get there.
Start to question and worry.
I get there quite a bit too. But no, at least this one, maybe I can say, yeah, this one needs to be an X right here. Basically, we can't have, Z was the term that's this core, like the Z score, right? So this is the area under the curve to the left of the Z score, but we have to integrate over some variable. And so when I do that and I hit save, it should go, there it goes. Is that better? Oh, thank you, yes. Remember this, remember it very seriously. Don't do what I do here. Did I tell you my story about my terrible preliminary exam or defense? Okay, can I tell you this? Those of you who are students, this was the most formative learning experience in my life. I had, so here at Iowa we have comps, we have to have a comps defense. That's the big, at least our program, I don't know what you guys do over in Psych, yeah. At Illinois we had qualifying exams that we didn't have to defend. Our big defense was our proposal for our dissertation. And that was in lieu of the comps defense, right?
Is that what it is here for comps?
No, not for, programs can change. You can do it that way, and actually programs, or even within programs, you can do it differently.
Yeah.
So the graduate college requires a defense type meeting, from what I understand. Mm-hmm. Now that can be defending your comps, could be defending your proposal.
Okay.
So we were defending our proposal. So this is a big deal meeting, right? And and I had this diagnostic model that, I'm like 2 years into understanding how to do all this, putting stuff together, and I put the most terrible notation together in my slides. And every time I would have a slide, Larry Hubert, who is a fantastic mentor, fantastic professor at Illinois, would just, before I could even open my mouth, what's that? Like every single slide. There was a part of the meeting, about 45 minutes, and I just sat down rather than present. I'm like, and I had a cooler, I get a drink, open up a drink, sit down. And no, but I thought I was going to fail. I thought it was done, right? Because the notation was so bad. And after the meeting, my advisor and the people who were like my advisor. Jeff Douglas was my advisor. Bill Stout was on the committee. Both of them are like advisors to me. Jeff was my advisor. Both also excellent people. Were being, trying to console me a little bit, saying, look, they weren't talking about your model. They were talking about your notation. And so ever since then, I've really tried to hit the notation. So when I have a mistake like this, I feel that a little bit of that defense meeting. But that experience, though, was key, because how often do you see notation that is sort of messy or clunky or whatever, right? You have to...
I mean, all of statistics, it's not consistent.
Yeah, it is really hard.
This is especially true coming from the math world.
I imagine, yeah.
When you go into stats, it's like, then you realize it's only 100 years old.
Right,
so,
yeah.
It's thousands.
True, but it was tough. So say this to you, Larry's way of saying things was always, the three most important words in real estate are location, location, location. The three most important words in psychometrics are notation, notation, notation. Always notation, because you could put a picture up, and that's relatively finite. But you put a model up, and there's infinite ways that you're basically describing what's happening, right? So
even our book, I think, has some sloppy notation sometimes, and it drives me crazy.
I agree. And again, I'm in their defense. I would also say it's a hard task. They chose to pick notation that was relative to each of the fields, right? So then there's no carryover across chapters, it seems like sometimes, or across sections of the book. The diagnostic model notation for the model I was doing, the log-linear cognitive diagnosis model, is nasty as well, and that's because how do you notate what potentially could be any type of effect for any type of levels of factorial, for a factorial ANOVA with general numbers of factors, right? So if you want the three-way interaction between factors A, B, and C specified as a regression constant, how do you get it? How do you notate that, right? It's a mess. So anyway, all right. We could do slope-intercept, though. Slope-intercept, our core in IRT is this whatever Logit. Here, I just want to double check. Nope. The slope-intercept version just multiplies the A through and changes things around a little bit. We get mu plus lambda I. You'll note sometimes people will put lambda, like the A times theta minus like a D. That would be where the item intercept is phrased as a threshold rather than an intercept. It's sort of a -1 times. I hate the thresholds, and since you can parameterize whatever you want in IRT, I made it all intercepts. I'm like, yeah, take that, thresholds. Sorry. Anyway, sorry. A world without thresholds. Thresholds are in prison. In my world, sorry. I get so irrationally angry over such arbitrary things. I feel bad for my children and my wife and everybody in my life. Anyway, at least we can laugh about that, right? Whoa! Thresholds. Yeah.
Cerulean blue? Cerulean?
What's that from?
That
oh yeah, that's right. Yeah, it's just, I can't believe it's this shade of blue. Yeah. Okay. So we have the cool thing about it is if you kind of match this up, when you multiply the A through, you can see where the conversion is, right? Lambda and A are synonymous because they're the thing that multiply theta. Lambda sometimes is called the slope. I like to call it the factor loading, but we also call this the slope-intercept parameterization. Mu would be -1 times A times B. So for an intercept, it's -1 times AB. For a threshold, don't even ask me. Whole crazy. Start turning green and veins bulging everywhere. You can also flip back and forth. So you can always go from one to the other. However, in Bayes, there's a catch. And that is, if you parameterize, let's say, slope-intercept, because that's where a lot of what we do happens to be mainly because of the multidimensional case. You put priors on mu, you put priors on lambda. And then you would say, well, in the process, okay, I want to run this model, you get a posterior for mu, a posterior for lambda. And let's say at the end of it, like M plus, you're like, you know, I'm going to go and make the IRT parameterizations. I'm going to multiply, I'm going to create my A, I'm going to create my B, right? And then your friend comes along, you know, that guy, right? Or person. Doesn't have to be a guy. And they say, well, no, I totally am a discrimination type of difficulty type of person. So I'm going to put a prior on A and prior on B. And you look at the shape of the posterior distribution for their A and B, and for the A and B that you found, and they're slightly different. Why is that the case? That's because, take a look right here. You're creating mu out of A and B multiplying each other, right? In the slope-intercept form, you're putting a prior on mu and lambda. In the discrimination difficulty form, you're putting a prior on A and B, and then you're multiplying them together to get mu. And so that's one of the key kind of differences in Bayes, where in the frequentist world, we're like, I don't really care. Here, whenever we want to go convert from one to the other, the posterior distributions might be slightly different. They're not likely to be wildly different unless you have some really crazy priors on things, but they could be.
I'm trying to think, if I should wait to the code, tell me to wait to the code. I'm trying to think, if you think that you're doing one, but you actually, you know, your first choice.
Yeah, right.
I give a prior to mu, but then I give a prior to also A and B. I'm overwriting my mu in the code. Is my mu going to change because I put also priors in A and B?
Ah, so you can't do all simultaneously.
Okay.
Yeah, so when you phrase a model, I guess you could make one item's A and B and one mu, but for a single item, you wouldn't be able to do both simultaneously. Yeah, so what's really going to happen is the code's going to sample an A and B from a single step in the chain, and they're going to produce a mu from that step. It's just what I'm saying is if you were to go with mu the whole way, if you drew the kind of the density graph of mu at the end, it may not look the same as if you did A, B and created mu.
Got it.
So, but in general, so that's the general caveat, and that's where I think just math would dictate that if you have a posterior distribution for A and a posterior distribution for B, and whenever you make a product, that's the big no-no, right? We get a delta method to get a standard error. Well, here we don't need a delta method. We have a whole chain of these things. We could actually go make a chain of mu and come up with that distribution. However, it will be of a different, slightly potentially different shape, depending on what does it depend on? How much influence of the data versus the prior, shape of data, you know, yada yada yada. There's all sorts of caveats, but I think in most typical use cases, as long as you have lots of data, you won't see a big difference. So I'm mentioning this because I'm not interested in most typical use cases. I'm interested in like the rare, like the small data size of it, and I think that's where the big difference starts to show. So it's interesting. The things that is making this lecture, and having taught IRT before, it's very interesting the difference between the two, like that comes about from it. Like if we were teaching everything in Bayes from the start in our program, sort of a thought experiment I do like every week when I teach, how would things be different? And like glossing over certain things, and when you get to Bayes, you don't gloss over them now. They're all the things that you sort of take for granted now. Oh wait, well, there's a catch there, and then, right?
Correct me if I'm wrong, also it's something you recently say about bypassing the need of using the delta method is not necessarily a bad thing either.
Also true. Delta method is the approximation, right?
You know, I got hung up with thinking on that when you mentioned that.
That's good. Yeah, so there's all sorts of little catches in Bayes that show up in practice. And I mean, they're in theory, but really you start to see them when you start, like you get your hands on distributions that you don't get to in other frequentist world. It's pretty interesting. Ben, you had a question.
Yeah, this kind of goes back to the very first slide and the name item response theory. So when we hear that, we often think of this, you know, ogive type graph or this logistic graph. But I just recently ran into Thurstonian item response models, and those don't use like a logarithmic or ogive link function, right? It's just a linear. And so really item response theory is theory underlying how students are responding to an item and predicting the item outcome from that.
Right, and I mean the roots of IRT, I mean it's like psychophysics phi gamma law, like interesting sort of the way it works, but simultaneously, the convenience of it, you had that sort of as a basic, but simultaneously you had effectively linear models that are generalized. And when the IRT really started to become really thought of as a foundation, you also saw that was similar to, not parallel with, but very similar to when coding methods of estimation and logistic regression were showing up. So you've got this big tie between the two. The Thurstonian models are interesting. They're not often thought of, but you see, I think those are the sort of the very, you'll find them in intellectual areas within like the Psychometric Society, like the case 1, case 5, the things that show up. I'm actually blanking on them at the moment, so I don't know that I can describe them very well. But no, I think the bigger picture here is for us, we're going to stick with what I'm used to.
Yeah, like,
so,
I
but you're right.
I just, a Thurstonian IRT looks just like CFA, pretty
Yep.
much.
Yeah.
And this essentially looks like CFA, but we have a link function. I'm sure you'll talk about that too. But
Oh, that's good. We're about to do that.
yeah.
I almost started class by saying, okay, I copied and pasted my CFA code, and I changed denorm to deburn. We're done. Have a nice day. See you later. I deleted a couple of parameters, and we're done. All right, but that's really what we're getting to. The other thing, I mean, there's sort of the history of psychometrics is littered with interesting stories of people being really confused on how to take CFA and do it with the categorical data. I think that was where you got it. I read a story about Lazarsfeld, who was there's a great book, 1968, Lazarsfeld and Henry, latent class analysis, mixture models, things that we now call finite mixture models. He was really instrumental in their development in the 1960s. And part of, I don't remember where I read this, and I don't even know if it's true, but I'm just going to repeat it without verification, so take that with a grain of salt. But it was effectively, he was interested in IRT models, but in the 1940s, but couldn't figure out how to go and make them work for categorical data. And this is prior to like Fred Lord's work in 1950 and so forth. And so he went a different way and just created the brand new set of models themselves. So it's an interesting, like this kind of the big limitation that happened to that 1920s to 1950s in psychometrics was, you've got people doing work in different areas. Classical was really big then. I mean, Cronbach's work, Gutman's work, so forth, Thurstone. But then also you've got another history to it. It's very interesting how it works. Anyway, yeah.
I have 2 sequential questions.
Yes.
The first one is, we have 2 approaches. We can specify A and B, or we can specify slope and intercept.
Yep.
That equivalent to same model but with different prior.
You could think of it that way,
yeah.
But because one of the things, it's a nonlinear transform because of this product right here.
Mm-hmm.
It's very hard to see. It's the types of prior are going to make a difference. It would be hard to specify the exact prior for mu that when you have like A being log normal and B being normal. Like a product of a log normal normal prior would cause a weird prior on mu, right? Yeah.
So, and the second one is, if it is same model with different prior, could we compare that with DIC or other techniques?
People do. I'm a little bit skeptical of it, and the reason being is that the prior distributions are on, I've learned them to be on different metrics, different scales, right? So this is one of the reasons in like in econometrics there's an issue. Like one of the things here, I'll give it to you. When we're doing CFA, and we have Likert type data, 5-point responses, like the example we had with the conspiracy data, which by the way, it's coming back next week. We're going to have the conspiracy. We're going to do IRT with it. We assumed conditionally normal for the response data, and next week we're going to assume multinomial for the response data with some type of order constraint, right? Which one fits better? And in econometrics, there's I'm used to an author's name, Wong is the name, that tried to come up with the theory of a test to see which would fit the data better. But you can't directly compare them through AIC and BIC, at least we're told, because the likelihoods themselves are on different scales because of the way that the distribution is phrased. So if you take that to Bayes, and you think about it from DIC point of view, when you talk about a posterior distribution, you may still have the same issue. But you see people doing it. So I'm curious. I don't know that I can endorse it. I can say it's often done, but I'm not sure exactly if it should be done, or I don't know enough about it. It's one of those places I've highlighted that I need to learn more about, and not there yet. It's going to come up, by the way, in just a moment when we look at unidimensional versus multidimensional, because the prior that we specify for theta, or for the hyperparameters of theta, is different. And you're going to see the DIC is massively different in these two examples. And yet, when you look at absolute fit, I won't want to spoil the ending, but there's a really interesting ending to this class. All right? The tease of what's coming up next. And then after that, the weather. Sorry. Our newscast in the United States, the weather is what most people watch for, so they've got to go and put something in front of the weather. Did that help? Okay. Other questions? All right, should we Bayes this thing? Let's Bayes this IRT model, but not with thresholds. We need to do what to make it Bayes? We need to talk about a model likelihood, or model data likelihood. We got to talk about prior distributions. So, model data likelihood. I don't know how, by the way, if you like this, where I can put little snippets of code in it, that's awesome. If not, if this doesn't work, I can switch it back. But here, what is the model? Well, what we're going to assume in IRT, because we only have, we're modeling binary data. And I say binary rather than dichotomous because binary implies 0, 1. So binary data, let's say one trial binomial or a Bernoulli distribution. So the conditional distribution of the data given theta is Bernoulli. I have here a unidimensional theta. It's going to be, without loss of generality, we can make this a vector, multidimensional. The probability, the parameter for Bernoulli is a probability. It's also its mean, right? And so what we're going to say is that the distribution function itself, in this case the probability mass function, is that probability raised to x times 1 minus that probability raised to 1 minus x. In JAGs, the function is dBern. D-B-E-R-N. They're not, it's kind of like Bernie. dBern is going to be at the Iowa Memorial Moon Union.
Feel the burn, Newly.
That's right. We are going to feel the burn on this one. dBern. We're going to feel dBern on this one. That's good. I like that. All right. It's kind of a socialist length distribution. Sorry.
Democratic socialist?
Yes, indeed. We all voted for Byrne here. Shouldn't mix politics and IRT, right? As long as you know I'm not endorsing anything here, it's more just...
I think you're endorsing some priors.
Maybe. Maybe. But here, each person and item is our index for our data. And in a unidimensional case, it's fairly easy to loop over people and items and make it dBern. And I just put a bunch of dashes here. This is where the model part goes. That's the core of the model. Actually, not the core, pardon me. That's the probability statement. So in there, you're going to have, if you want a 4PL, you're going to have C, D, yada, 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 right?
Because technically the conditional likelihood up there should include those model parameters as well, right?
Right. Anything that specifies the probability of the item response being 1, and in our case, that's everything on the right-hand side of the equation for IRT. It's the inverse link transform model. So in slope-intercept form, looks like this with a Logit link. And with a probit link function, which, by the way, I'm going to use all of our examples for, although your homework is in Logit. One small catch, not a big deal, not really that hard to implement. You'll note here I didn't do E over 1 plus E because I was running out of room, but you can make the result 1 over 1 plus E with -1 times the core is equivalent. And down here as well, the function that is in JAGS that does the probit link function is PHI, phi. That does the conversion for us. And I will note out when we get into the data that this part for phi is when you specify the model with phi, if we go and look at the samplers for it, we'll see it's called Holmes and Held, which is a good thing. That's that data augmentation Gibbs sampling. We don't get that in JAGS when we switch it to Logistic. Doesn't mean it's bad, it's just a different sampler altogether. Questions? The art of MCMC is how fast you want it to go and how nice it samples your posterior. If you've got all the time in the world, you can just do the most inefficient algorithm you want and still sample it, just hopefully. Life is short, though. Here, we could do the same thing with discrimination and difficulty, blah, blah, blah. So about priors now. The ability parameter, we can standardize it with the d-norm. Or we can go and estimate variance. Here, we have to, though, say the variance is gamma. Right. But remember in gamma, this is one of the things that drove me nuts. I don't know why it's making this on a new line for my text right here. This is small little features of the R world with the interplay with math jacks to put LaTeX in. But it's hard to determine when we go and do. So here's the difference between our world in IRT and our world in CFA. If we did a unidimensional CFA, our variance would still be d gamma, right? Inverse variance, make it a conjugate prior. And we could talk about what that variance would be, right? That variance was going to be part due to, like when we had a marker item, part due to the variance of that item. And so that's where I anchored that as my specification. Technically speaking, I could have worked harder. Oh my goodness, it fit now. When we go to the Logit side, it's still true that the variance for the factor comes from part due to that marker item, but it's less clear as to what size it will be. Yes, we could probably come up with a link transform, or a delta method transform variance that we could go and see what it would be, but I just gave up and said, I'm just going to give you the value of 1 there, or something like that, just randomly. So we could also do the mean as well. The mean could be normal. Prior distributions for the mean aren't as hard. The nice thing about, so the bad thing is we had a hard time speculating what the variance is. But one of the good things of being in the link transform world, either with Logit or with Probit, we kind of know the upper limits of these things are going to be. Because once you have a Probit that's bigger than 4 or less than negative 4, you really have a probability that's really, really tiny. You're not going to see many parameters for, mu is on the scale of that, right? And so you're not going to see many parameters go outside that range unless there's something really crazy with the data. So you can come up with priors that sort of make that happen. And what you're going to see with my priors, I went from, in the normal case, I had this huge, massive variance, like 1 million for the prior. And I'm going for a flat prior. In this case, because we're on Logit or Probit scale, I cut that down considerably. And for the MERT model that's at the end, which is, I think Lisa, I might hear her being mad through the screen about the example I'm going to give you, but just want to show you it could. I cut that down even more, right? So that's, you're going to, why that's the case, if you remember in the regression and CFA case, the slope, sort of what you would expect the slope range to be, remember it's the variance of y over variance of x, effectively, right? Well, in each of these cases, y has its variance limited and truncated. In the Probit case, the variance should be 1 or close to that. In the Logit case, it's actually pi squared over 3 or somewhere around there. There's a piece of trivia for you. Okay, blah, blah, blah. Questions? Okay, for the A parameter, this is where we could do a log normal, which is DL norm, or a normal with a truncated. I will note, in my syntax today, I found a way to make R to JAGs do reproducible results. I should have read the effing manual, RTFM. I think that's what
Small difference.
yeah. You have to set the seed if you're doing it, but the other thing I'm going to do is use parallel processing with it as well. So we're going to save some time. It's going to run each chain in parallel. Why I'm saying that is the R to JAGs parameterization uses the function. If you specify the function in R, you cannot truncate within that function or do it well. I haven't figured out the catch to do it. There may be something in the R to JAGs manual for it. But R will throw a fit about T, 0, and a comma because you left an argument out and it's looking to make that a function. So if it's in quotes, you can do it. If it's in a function, good luck. I prefer the unrestricted prior. You'll find out that that's unrealistic. If you take the L out of my DL norm in the example today and run it, you'll see all sorts of multimodality showing up. So, item difficulty parameters, range of those. We can keep those normal. They go negative, they go positive. Same with item intercepts. Lower asymptote parameter. Okay, I don't know why I'm wasting my time talking about C, but C shows up popular. Back in the day, there was a program named Bylog. It does still exist.
I've used it.
Oh my goodness! Do you remember, like, you had the formatting files and all the stuff to make it work? Did you use it in your classes here? Or? Yeah.
You gave us an option with Dr. Colvin. You know, you can use FlexMerge or whatever you wanted to do, and I'm gonna go.
That's good. Bylog had a default for the C parameter that had a beta prior. So back up. C parameter ranges between 0 and 1. We expect it to be on the low side. The Bylog default, which I grew up with, so I had to note it here. Beta has two parameters, A and B, or alpha and beta, depending on who you're talking. And what it did was, if you took like the chance probability someone got an item right, if you had a 4 option, they'd say like 0.25. It made the A parameter 20 times that chance plus 1, and the B parameter 20 times 1 minus that chance plus 1. And what that would do is effectively put the mode of this distribution right over that chance point for the prior. You're going to wonder what's the spread, why is it 20? Our text goes into it a little bit in Roy's chapter, but it's the reality of it is this C parameter is really, really hard to estimate even, and that's why Bylog had to go Bayes for it in the first place. So, hope that helps. Okay.
Of course, obviously better if you have lots of data.
Oh yeah.
But if you have a little bit of data, like the ML sense of standard error is huge.
Yeah.
Gigantic.
Yeah, it's a pain. D parameter, I don't know what to do with it. By the way, beta distribution is D beta in JAGs with an A and a B that show up. And then the D parameter, use a beta, that's what I'll say. I don't know what it should be. You could go and play with the code and put a D in there if you want while I'm talking. I dare you to do it while I'm talking, see if it finishes. See what happens. It makes it sound, see, I thought that's the way you do it. Or better yet, I bet you can't get that to work. Oh, look at that, I got it to work. That's how it works for me, right? Oh, you can't do this. Oh, watch. All right, so let's go to our example. Any questions, comments? Yes.
So
Yeah.
usually in the IRT scale, we use 1 point explanation and 1.7.
Yes.
So in your specification,
I don't specify it.
so
You'll see in the research world, that's gone away for the most part. It's dead. I think in other parts of the world, like the history of it, some of the first programs that were out there to do IRT were Probit based. And so if you're in a testing company using Probit and all of a sudden you switch to Logit, you want to have comparability, I think that's where it shows up. You can still put that in the code if you want. It's just a constant, rescales things. But I won't for anything I do.
so the things we get from this specification, if we want to get the IRT like kind of common scale, we have to divide by 1.7.
In S, yes. In Probit, you divide by 1.7. Yeah. I don't. Like, there's from this point of view for us, why would you need it?
Yeah.
It doesn't do anything, right?
No, it's just a rescale, right?
Yeah, exactly right.
So that's where I say, like, I think if you see in the scientific world, you don't see papers with it showing up anymore, or you do, it's like people who have been, that's how it's done. But realistically, like, theta is theta. We're not comparing it with anything else. We just have a group, we have a study. And pretty much every use case that we use it for would be like that. And now, if we do need to combine or whatever, yes, we may need that option to do so. But that's it's a good, very good question though.
Yeah, I think like in FlexMart they did in this way, so we have to kind of divide by 1.
Yeah. So that's sort of what happens. You get people who run the package. Now you create the code here. So if you want the threshold back, you make it a threshold. You want the 1.7 back, you put that back.
Or a 7.1.
Ah, forget it. You could do whatever you want. This is your world. You're coding it. Right? You want to tell me, oh, Templin, I want 1.7. No, I think I'm trying to make a joke. It's a very good point to make, though. And one where, depending on where you're working, depending on what you're working on, you may have to consider. It is just as simple to put it into the syntax. When you specify the model itself, right here, if you wanted to go and put the 1.7 in, you'd put it in the same place outside of the A that you'd see it before. Or if you wanted to keep this to where it needs to be, you take this whole term within the phi function and divide by 1.7. That's basically it. And you are the boss. And if you do, and for homework, I didn't specify it, so if you want to scale it that way, do it. And if you want to scale thresholds, do them. That's fine. I'm only saying that because in teaching thresholds, I always default to intercept, and I get the direction wrong. I get so frustrated by that. Any other questions or thoughts?
Actually, I trained the similar code for my research. And then I also saw another person's code, and then they kind of set restrictions for parameters. For example, for A parameters, they gave like they estimated freely for example, if the number of items is n, then they freely estimated n-1 A parameters, and then later they set for the less difficulty parameters to be just 1 over the multiplication of the other discrimination parameters.
Right.
I actually tried both. And then I did not really good estimates for the later approach for the restriction one. And then so I freely estimated just all the discrimination parameters like you did. And then I actually did not understand why we set such restrictions.
So there are a couple different versions of it. So it depends on the model, and I'm not familiar with that restriction as much, but there are other ones that you'll see that I'm going away from here. They talk about, the book talks about a little bit, which is a hierarchical parameterization, where they say, I'm going to say that all of my prior for the A parameter, you'll see this quite a bit actually. They'll say, instead of fixing these hyperparameters, they'll try to estimate them. And they'll try to do that because they'll say, well, this helps focus what the normal distribution be. Maybe they're going to be common from a common distribution in a test. And that may be something that was done there, or may not be. I don't exactly know. I'd have to see the example to figure out why that is there. The other part could be that they want to keep the variance of theta to be a certain number or something like that.
Yeah, it sounded like instead of using the sum equals 0 constraint, they just used a different constraint to make sure they could identify it.
Yeah.
It's a again, without reading it, it seems like a less intuitive constraint to me.
And there are constraints with multiplications. It's just an art, the use case of it, right? So I'd be happy to look at it afterwards if you, or maybe some other time to talk about it some more if you'd like. I will mention that hierarchical parameterization. Give me a chance to talk about it. So thank you for. I'm trying to talk about a different topic. maybe you've seen this before, where they try to estimate these values of the hyperparameter distribution. That actually gets into a really interesting use case of these models that start to butt up into cross-random effects models. And I don't like specifying the models that way as much for several reasons. But first of all, if I'm coming about this, I don't need to have, it sort of links all the A parameter, or all the classes of parameters together under a single uniform umbrella. And I'm not guaranteed that they need to be that way. I'm sort of treating these, I want to treat these as the analog of something that's its own value and its own fixed term. When I make a hierarchical parameterization, I basically generate those to have some type of dependency with them. I just try to keep them separate. So I'm not going to go into that much, but it's an interesting world. We open that door and we can, I think, G-theory this stuff. We can go down and estimate variance components for each of the types of dimensions we may have, but I'll leave that right now. Hey, look at that, it's break time. Let's take a 10-minute break and we'll come back and example it up. Thank you.